Hello everyone, in this project I built a binary classification model to predict whether a person has a pre-diabetes or diabetes. Because the data set is imbalanced, I use F1 score as the evaluation metric. My final model is a His-Gaussian boosting classifier with five-fold cross-validation and threshold turning. To improve model performance, I focused on four areas. First, I choose a boosting tree model. Boosting models work very well for structured, and because they can capture nonlinear relationship between variables. Second, I turned important hyperparameters such as learning rate, tree depth, and regularization, and this helps the model learn more complex patterns while avoiding overfitting. Third, I handle the class imbalance using balanced sample weights. This makes the model pay more attention to the minority class. And finally, I adjust the classification threshold instead of using the default value. This helped improve the F1 score. So I test several different models before choosing this final one. I tried a logistic regression, catapult, and his, and logistic regression is simple and easy to interpret, but it cannot capture complex nonlinear patterns. Catapult is powerful and performs well on many uh tabular data sets. However, in this case, its performance was not as stable. So therefore, I selected as my final model. And so the data set is imbalanced, meaning there are fewer positive cases than negative cases. To address this, I use balanced sample weights during training. This ensures that model does not ignore the minority class. I also turn the classification threshold after training to maximize the F1 score. And to evaluate model performance, I used five-fold cross-validation. Stratification ensures that each fold keeps a similar class distribution as the full data set. Compared to the simple chain test split, cross-validation provides a more stable and reliable estimate of model performance. And to improve model fit and reduce overfitting, I use early stopping. The training process stops automatically when validation performance no longer improves. I also apply the L2 regulation to prevent overly complex trees. These techniques help improve generalization to unseen data. So the confusion metric helps us understand prediction trade-offs in a healthcare setting. Predicting uh, risks as real consequences, and false predictions may affect medical decision or resource allocation. By turning the decision threshold, we can balance model prediction to better align with the practical needs. And so if I have more time, I would explore additional improvements. So first, I would try um, ensemble stacking by combining multiple boosting models. And second, I would include additional external data such as health-related information. And third, I would design a monitoring system to detect data drift and retrain the model when necessary. So in summary, I built a boost boosting based classifier using cross-validation and class balancing techniques. And through hyperparameters turning and threshold adjustments, I improved model performance and stability. And I thank you for your listening.